Hi and welcome back. In this video, we'll be discussing about etcd cluster, what it is, why we use it in Kubernetes, and what benefit it brings over the other distributed database system. We are going to learn about Raft Consensus Algorithm with little animations, and finally look how etcd cluster works on play.etcd website. So let's start our journey. So let's talk a little bit about etcd. etcd is an open source distributed key value store for the most critical data of distributed system. It is distributed by replicating data to multiple machines, therefore highly available against single point of failures. Using Raft Consensus Algorithm, etcd gracefully handles network partitions and machine failures. In fact, it also handles the leader failures. etcd stores Kubernetes configuration data and state data. It has watch function that compares these two data. If they ever go out of sync, etcd will at that instance inform Kubernetes API server, which will further take action by connecting with controllers. etcd is widely used in production at CoreOS, Kubernetes, YouTube daemon, etc. We have different ways to set up our etcd. We can install etcd as a pod in our Kubernetes master, and this image shows you the same that how it works. Each of them has their own benefits and has their own pros and cons. So the another one that we can think of is we can separate the etcd from Kubernetes cluster, and we can create another etcd cluster for highly available and highly secure and resiliency. So this is another way how we can create our etcd cluster. The following sequence diagram is taken from Heptia's blog. It shows the components involved during a simple pod creation process. It's a great illustration of the API server and etcd interaction. So what happens when a person creates a pod? When you write kubectl create pod command, you say API server to create a pod. API server writes that to the etcd database, that is pod, and then it returns it when that is stored in the etcd database. It responds back to API server, and API server responds back to you that your pod is created. And then API server sends a watch notification to the scheduler, means that scheduler should assign a node to the particular pod. Scheduler writes back to the etcd database and assigns a assigns a node to that particular pod. And then kubectl wakes up, and means the API server sends the watch notification to kubectl. It wakes up and then runs the pod and do whatever the further thing it needs to do. So let me show you a great demonstration that I've taken from a talk that is by Patrick Trock. And what it says that when a person uses the deployment, when a person applies deploy.yaml file, or it can apply patch file, anything, then API server first of all it adds that information to the etcd, and then it sends the watch event to controller, deployment controller. Deployment controller says that scale up the new replica set or scale down the old replica set based on whatever information you have provided. And then that is returned back to the scheduler, means a watch event has been sent to the scheduler, and scheduler again updates the pod. Then a watch event has been used to be sent to the kubelet that is inside the pod, and then kubelet takes particular action to update the pod. Similar happens when you delete the pod or create a new pod. So this diagram illustrates a lot about what happens, and you can think of watch event as a webhook. Means it's not exactly that, but you can think in that way also. Like whenever something happens in an API server, it assigns, it creates an event, and the person who the components that are registered to that event gets activated when a particular event occurs. We have an ETCDCTL, means ETCDCTL command that is actually a command line interface tool written in Go, and that allows manipulating an etcd cluster. It can be used to perform a variety of actions such as set, update, or remove keys from the etcd, verify the cluster's health, add or remove etcd nodes, generating database snapshots. You can play online with a 5-node etcd cluster at http://play.etcd.io, which we are going to see. There are lots of resources that I'll share with you in this complete demo. So what we are going to do next is we are going to learn a little bit about Raft Consensus Algorithm, on which the etcd runs. So let's go through that. And I'll discuss all these resources with you so that actually these are the important ones that I found on the internet, which helped me to understand a lot about etcd. So I'll share everything with you. Now let's talk a little bit about Raft Consensus Algorithm. For now, you understand consensus means agreement, right? So it's the agreement between different nodes, nodes of the cluster, etcd cluster. Let's say we have a single node system. And for this example, you can think of our node as a database server that stores a single value. Suppose that we have a client that can send a value to the server, and that value is going to be 8. Let it be. Now, coming to an agreement or consensus for a single node is very easy, right? There is only one node and one data needs to be, only a single data needs to be updated on a particular node. So that's easy. But what happens when we have multiple nodes in our system? How a consensus algorithm, how a consensus is going to be achieved? That's the problem of distributed consensus. Raft is a protocol for implementing distributed consensus. Let's look at high-level overview of how it works. A node can be one of the 3 states. It can be the follower state, a candidate state, or a leader state. All our nodes starts in the follower state. If followers don't hear from a leader, then they become a candidate. The candidate then requests votes from other nodes, and nodes will reply with their vote. The candidate becomes the leader if it gets votes from the majority of nodes. This process is called leader selection. All changes to the system now go through the leader, and all changes, like suppose I want to set a new data, so it will be passed through the leader. Each changes is added as an entry to the nodes as a log. So suppose I want to add 5 to that particular node, then it will be added as a log. The log entry is currently uncommitted, so it won't update the node's value. To commit the entry, the node first replicates it to the follower nodes. Then leader waits until a majority of nodes have written the entry and pass it back to the notify back to the leader that okay, we have got the value. When majority of nodes sends the value, leader commit its value to the node and change its state to 5. The leader then notifies the followers, and the followers then commit their entry. The cluster has now come to a consensus about the system states. That is, all of them are having 5 as their value, right? As their state, you can say state or value, anything. This process is called log replication. Next, we'll see leader selection. In Raft, there are 2 timeout settings which control selection. The first is known as election timeout. The election timeout is the amount of time a follower waits until becoming a leader. The election timeout is randomized to be between 150 milliseconds and 300 milliseconds. So in this case, you can see that there is a timeout going and node C becomes a candidate, right? So after the election timeout, the followers become a candidate and it starts its election term. Votes for itself. So first vote, it votes for itself. And then sends out request vote message to the other nodes. If receiving node hasn't voted yet in this term, then it votes for the candidates. And the node resets its election timeout. One candidate has a majority of votes, it becomes a leader. The leader begins sending out append entries, that is also called as heartbeat message, to its followers. These messages are sent in intervals specified by the heartbeat timeout. So first was election timeout and the second one is heartbeat timeout. Followers then respond to each append entries message. And this election term will continue until a follower stops receiving heartbeat and becomes a candidate. So what is the case when they won't receive a heartbeat? The case would be when leader goes down, right? There is some problem and the leader node goes down. So in that case, again, that process will continue and a node will become a candidate and it will receive a majority of votes to become a leader. Let's stop the leader and watch re-election happen. So our node C went down and now node A becomes a leader, means becomes a candidate, and then it sends then it asks for the vote from the other nodes and then receives the majority votes and becomes a leader. Node A is now leader for term 2. Requiring a majority of votes guarantees that only one leader can be elected per term. If two nodes become candidates at the same time, then a split vote can occur. Let's talk about what is split vote and think about it. Suppose we have 4 nodes and 2 of them become a candidate at the same time. Okay, so you see that 2 nodes both start an election for the same term and each reaches a single follower node before the other. Now each candidate has 2 votes and can receive no more for this term. The nodes will wait for a new election and try again. Okay, so now you can see, right? Now, node B received a majority of votes in term 6 and so it becomes a leader. Log replication. Once we have a leader elected, we need to replicate all changes to our system to all nodes. This is done by using the same append entries message that was used for heartbeats. Let's walk through the process. First, the client sends a change to the leader. The change is appended to the leader's log. Then change is sent to the followers on the next heartbeat. An entry is committed once the majority of followers acknowledges it, and response is sent back to the client. Now let's send a command to increment the value by 2. So B node has been added to, you think 2 has been replicated in both of the A and C nodes, and finally B node has committed the value and again sent the heartbeat that I have committed the value, and the follower nodes also committed the value. So the system's value now is updated to 7. Raft can even stay consistent in face of network partition. Let's add a partition to separate AB and CDE. The problem here is the upper part have 3 nodes, right? So they can talk about majority, but below one have only 2 nodes and there is no term like majority. Because of partition, we now have 2 leaders in different terms. Let's add another client and try to update both leaders. Now one client will try to set the value of node B to 3. Node B cannot replicate to a majority, so its logs entry stays uncommitted. The other client will try to set the value of node C to 8. This will succeed because it can replicate to a majority. Now let's heal the network partition. Node B will see the higher election term and step down. Both nodes A and B will roll back their uncommitted entries and match the new leader's log, that is 8. Our log is now consistent across our cluster and the value is set to 8. So that was all about consensus algorithm, Raft consensus algorithm, and how it works. And this is what actually happens in ETCD cluster. So we have one more lab that you can see, you can play with. ETCD cluster is at play.etcd.io. So here you have a 5 node cluster, right? and you actually want to start all the nodes. Let me start all the nodes first. So I have started all the nodes, right? And in our case, the leader is node 5. And suppose I want to enter any value in node 3, right? We can add any value. Now here you can see that there are endpoints, and we can add any value to any endpoint, right? Suppose I am not adding this to node 5, as you have seen that what will happen if we add it to node 5? Node 5 will send these values to logs as a log to other nodes, and until it receives the majority, that majority of the nodes have been updated, it won't commit its value, right? And then majority of the nodes will commit, means when it will send the heartbeat, the majority of the node will commit their value too. But what will happen if I am sending the value to node 2? That is not a leader. So let's add animal as a key, and let's make it as lion. Okay, and now let's submit this value. So here you can see that our write is successful. And what would have happened when you add any value to node 2? The log is added here, right? You have seen that it adds as a log, and then it reports to the leader node that I have a value has been changed inside me, a state has been changed inside me, and then leader sends to the other nodes that okay, you need to change your value, and then other nodes also add it as a log. And finally, they all respond back to leader saying that, hey, we have added the new value animal as lion, means key and value as a log, and we have updated our state. So then node 5 will commit the entry and will send the heartbeat to other nodes, and other nodes will commit their entries, and finally will respond back to the client. So this is what happens. You can delete the node in a similar way. And what will happen if we one case that I want to show you is what will happen if we just have 2 nodes, right? In that case, what will be the problem? So let me stop other nodes. I'm stopping the node 1, node 2. One more thing that I want to show you is the state of this node is follower, and the state of node 5 is a leader, right? Okay, and actually I want to turn off the leader also. So let me stop the leader, and now node 4 becomes a leader, right? And now suddenly you see that it becomes a follower. So what is going behind this thing? The reason is why it becomes a follower again is because it didn't get the majority vote. And now if you try to enter some value in a system, it will throw an error because they cannot write the value. And suppose I want to change the value to animal lion to tiger, and let's try to update it. So there is no leader in the system, and you'll see an RPC error code that unknown DESC Raft stop, right? And once you start this, restart this cluster. Okay, so once you restart this cluster and a node is selected, means a leader node is selected, you can see here, right? And now if you try to write this value, you'll definitely see the value has been written here. So this is how ETCD cluster look like. This is a 5 cluster which you can see here and which you can play with. And there are informations given on how you can install the ETCD with lots of informations. You can find lots of information here, how you can download the package and install it. We are actually going to use the systemd one, where we are going to add these things in our systemd unit file, right? So this is what we are going to work with. One other resources that I want to talk about is you can find a lot of information on operating ETCD cluster for Kubernetes. This is specific to Kubernetes, and this is the documentation, GitHub documentation at ETCD, and it's inside the operational guide. And here you can find that how many nodes you need, what should be the size of the cluster, what should be the size of the node. For small clusters will serve 100 clients and fewer than 200 requests per second. So there are lots of information given here which will help you set up your cluster as per your need. So, and what kind of instance you need. For AWS, you will need m4.large for small cluster and m4.extra large for medium clusters. You can find lots of information here. And the complete operational guide can be found here, where you'll see how to handle the failure situations and authentications and gRPC proxies and the visualizations that is in Grafana, and many informations. How you can achieve all this, you can find it here. So that's an operational guide of etcd. And one of the great resources that I found was from IBM, where they have explained a lot about etcd cluster, and this was a video. I first watched this video to understand what is etcd, so you can go for it. All the links will be provided in description. So that was all for etcd. I hope you understand what is etcd and how it is going to help us to in our Kubernetes cluster. And one important part of etcd is watch function, because etcd continuously watches for any changes in the etcd cluster, right? So that is important. Hope you enjoyed this video. Thank you.